Back in action. So next up, we have Anthony Clark. Anthony has been a cybersecurity researcher for over 20 years. He was a researcher at Los Alamos National Labs and is currently a guest scientist. Welcome, Anthony.
Hey, how's it going? So a little bit more about my background. I founded the Red Team at Los Alamos. I was one of the original CSERT team members. I built the technical security program for the Nuclear Weapons Division of the lab, and then I founded a number of companies. Right now I'm running a company called Red Pro Lab. One of my previous companies, I did consulting for a hedge fund called Bridgewater Associates, and they have a concept called building a machine, which is a way of designing a process around what you're doing. In their case, it was around stock trading. And so what my talk is about today is we built a machine process around reverse engineering hardware and software. And the reason for this is with the Internet of Things, avionics, drones, industrial systems, the internet and network communications are prevalent across so many devices that there's a large need for security assessments at the hardware level. And we're assessing so many devices that we needed a rapid process to be able to do it. So that's what I'm going to cover today. And our specialty is taking technologies that we've never looked at before, learning how they're supposed to work, reverse engineering them, and leveraging them in some way for attacks, effects, vulnerabilities, things like that. And then the types of devices that we're looking at are scientific instruments, avionics, machines, in-flight entertainment systems, physical security systems like electronic locks, the type you might have at your hotel room. We've worked on General Motors and Hyundai automotive systems, reverse engineering their passive entry, passive start, for example. So this process applies to across the board on all types of hardware systems. So this graphic gives you an overview of what this process is that we've developed. And I'll give you a high level, and then we'll kind of dig into details on each one of these areas. So when a new device comes into our lab, the first thing we do is catalog the device, collect all of the information, make, model, manufacturer, dimensions, high-resolution photographs, inside and out, all of that type of information. And the next thing that we do is an open source review, which is where we look across FCC databases, vulnerability databases, vendor websites, anywhere that we can get information about the device that we're assessing. Once we've covered that area of information, we do a RF, radio frequency assessment of the device. And I'll show you some slides later on what that looks like. But essentially, we take the device, put it in an isolation chamber, and record any emissions that it makes or any communications using Wi-Fi, Bluetooth, Zigbee, other protocols. Are there things that we can do to it from an RF perspective as well? Then we do a full network survey of the device. How does it communicate on the network? Does it have services, web APIs, things along those lines? Our next step is a hardware analysis. We're looking at debugging ports, chips, memory, where it's storing its firmware, inputs and outputs to the device, all of those sorts of things. Once we have all that done, our next step is software analysis. And this involves downloading the software from the vendor, dumping software from the device itself, and then running that through a reverse engineering process where we're looking at potential vulnerabilities, ways that the software is used, debugging capabilities, things like that. And then we build tools. So for example, in a pen testing environment, you might be using tools like Metasploit or Nessus or any of these kind of off-the-shelf tools that you use to scan networks and software. From our perspective, we're usually building custom in-house tools because the device that we're looking at doesn't have anything available in those runs. The next step is to build a knowledge base. All of this information becomes useful when new versions of the device comes out, other types of devices that use similar hardware components or similar software. So we build a large knowledge base that we can refer to as new devices come in. And then finally, my favorite phrase is, if we didn't document, we didn't do it. So we document all of this and provide it to our customer at the end of the process. All right, so in order to enact this process, you have to have a lab to be able to do all these different steps. And the way that we've approached this is a bench concept, where we have a bench for each one of these things. So for example, we have an RF test bench where we collect any signals leaving the device. We have tools for all the different protocols that can be seen in the device. We have a virtualization infrastructure because often we have to emulate the device's software, or many of the devices that we look at are based on ARM. And so having an emulation capability for ARM where we can do destructive tests without actually affecting the device itself is very useful. And then our hardware test bench. So for lab equipment, what are the types of things that we use? These are some of the basics in this screen. We have logic analyzers, we have oscilloscopes, we have multimeters, and alongside that, a whole host of different types of gear. So being able to isolate the device on a standalone network or air-gapped network is important. Many devices these days communicate back to the vendor, and if you're doing destructive tests or offensive tests against the device, you don't want to impact a vendor or another customer on accident. So doing all this sort of testing in an isolated environment is key. We also have a host of small programmable devices that we can use to affect the hardware that we're testing. These might be Arduinos or Raspberry Pis. In some cases, we have USB devices that we plug in order to emulate keyboard effects. One good example of this is with avionics and flight entertainment equipment. If you've ever been on a plane that has a little movie screen on the back of the seat, a lot of times those are running an Android operating system, and there are secret sequences that you can do to get into the operating system of the panel. And so having a USB device that can emulate a keyboard is helpful in attacking those. Also, in addition to those sorts of devices, we have an imaging bench where maybe we want to take a very close look at the device's hardware components, chips, CPUs, network traces, and so you're going to need something along the lines of a electronics microscope. We also have high-resolution cameras for taking close-up pictures, and I'm going to walk you guys through a case study of how all this works. So with such a complicated process, you also need a way to track what you're doing, track your steps, coordinate between different team members. We have a hardware tech, we have a software person, we have a reverse engineer. And so you want to build out a board or a process for tracking everything that you're doing when you're doing this hardware testing. In our case, we use what's called a Kanban board. It's usually used in software development. But we use it for tracking the steps that are described in the diagram earlier. So this is an example of what target cataloging looks like. In this case, we're targeting a Medtronic's medical device. And so what we do is we do a teardown of the device, documenting the steps, what tools do you use, what size bit do you need to remove the proprietary screws or whatever, what inputs and outputs the device have. So in this example, you can see we've got a phone line input, we've got power, and then we have connections to other types of medical devices. We catalog all this information in our knowledge base, including any data sheets that apply to the components on the board. If there's difficulties in removing the case, sometimes this hardware will have security features, such as a coating over the chips to prevent you from pulling them or identifying what they are. So that's the catalog step. Then we dig in really deep to specific key components on the board. For example, EEPROM, NAND flash, anywhere where the firmware might be stored on the device, as well as key CPUs, FPGAs, and then catalog all of the pins and configurations for these different components. because these are critical in the attack phase of this process, where we're trying to find ways to compromise software. Just briefly, this is what the open source review might look like. There's a FCC ID database for any hardware devices which use radio frequency communications. And a lot of times you can find a great info there as far as, frequencies, interference, noise. They do a great job of testing radio frequency devices, and so you can leverage some of that information. So for the RF survey part of the testing, we have an isolation Faraday cage. Normally we don't have a laptop in the cage, but it made it easy to demonstrate and photograph. And so you would put your hardware device in here. There's ports for antennas, SMA ports, and then you're going to measure a few different things. You want to see what the device does when you power it on. Does it make any radio communications? You also want to see what the device does in normal operation. So user interacting with it, connecting to it over the network, does it generate any emanations there? And so we use a spectrum analyzer. Our Faraday cage goes up to 6 gigahertz. We typically don't see too many devices going above that, but it is possible. Emanations indicate potential attack surfaces or areas where you can snoop on traffic. And for our Faraday cages, we have pass-through ports for network, USB, and power. That way you don't have to have penetrations in your RF shielding. So there's higher and sophisticated tools for doing this type of work. I'm going to talk about the types of tools that you could buy as a consumer or a hobbyist. So for our lab, we have things like the HackRF1 running in spectrum analyzer mode, and that's what you see here, collecting emanations from the device. We have tools for RFID, tools for Wi-Fi, tools for Bluetooth, software-defined radios, all of that sort of thing. One additional thing that can be very useful in this kind of testing is what we call near-field analysis. This is where we place a probe very close to components on the device board. So in this case, this is an example. We have a Raspberry Pi, and we have a near-field probe, just a few millimeters from the CPU at a specific angle. That gets attached to a high-gain, low-noise amplifier so that we can pick up any radio emanations coming from the device. And then that's connected to an oscilloscope in spectrum analysis mode. So this lets us collect very fine emanations coming from the device. And what's interesting about this is that you can actually tell the difference or fingerprint different processes running on the device. So for example, we put a crypto miner piece of malware on the Raspberry Pi, and we could distinguish that from, say, Apache running on the Raspberry Pi. So doing that level of monitoring, you can actually fingerprint processes running just by what's leaking off the CPU. Now for the network survey portion of the testing, this essentially involves running network scans, doing full packet captures, very similar to the RF approach. Device goes on an isolated network. Every single thing the device does from a network perspective is captured and cataloged and analyzed. We have a bunch of different ways that we do network tapping. This here is Hack5 Plunderbug. It's a very small, it's like a USB key that you can attach to the network input of the device and capture all the traffic. Now, why we do this is things like a lot of these devices, especially Internet of Things, industrial devices, their security is about at the 1990s level. Often they don't use encryption for the network communications, and you can capture things like clear text passwords, which this is an example of that, for the web server that's running on that device there. Next, something people are probably more familiar with, just regular vulnerability scanning. In this case, we're running a burp scan against the device's web server, looking for kind of low-hanging fruit vulnerabilities. As the previous speaker said, oftentimes you just need donuts. You don't have to go to really extreme lengths in order to compromise a lot of this hardware. In this case, the session token is available. This device doesn't use HTTPS. The session token is in the URL that's communicated by the user. We can capture that off the network and then recap it. Once we have an understanding of how to communicate with the device from a network perspective, the next step is to locate potential effects. So what this particular device does is it's a network controlled power strip. So like in our lab, when we have devices under test, we don't want to be going in and plugging and unplugging, turning things off and on. It's helpful to automate that process. For example, when you're doing the RF testing, you want to be able to remotely turn the device on and off in order to capture the RF emanations. So this device is network controlled. So we're looking for effects against that device in order to do something that is unexpected. In this case, from capturing the web application traffic, what we identified is the user just sends a command via the URL to turn the power port on and off. And there's no real authentication or protection on this command. And so our next step is to build a tool that we can run, in this case the Python script, which sends the same command to the device over the network and turns the power off on the device. So I've seen these we did some work for a satellite company, and they were using these in their test lab, and we could turn off their satellite sensors remotely just using this effect. All right, now for the hardware analysis phase. This essentially involves disassembling the device, looking at the circuit board, and trying to identify anything that we can use to attach to the device and interact with its firmware. So these might be JTAG debug ports, UART ports, SPI ports. And there's a web database called JTAG Test that provides pinouts for a lot of these different debugging ports, so you can go look those up. In our case, like if you look at the middle picture there, one of the first things that we do is take a multimeter and measure every single pin that we're able to access on the board in order to identify which pins are likely to have data, transmission, which ones are ground, things along those lines. And this is what our pinout analysis table might look like at that point. So after we've touched every pin on the board, we're writing down every value that we find and trying to identify what could we hook up to where might we be able to have an effect. One of my techs made this. So this is using the Sally logic analyzer. And what you do is, we use the Raspberry Pi for this example as well. You connect the logic analyzer to all of the pins on the board, and then you power up the board, and the logic analyzer will actually tell you which pins have data on them and which ones are likely to be ground. So it's an automated way of doing what I just described in the multimeter. The other thing that you can do with the Sally logic analyzer is decode data that is being transmitted on the pins. So in this example, we were transmitting hello world on the pins and able to capture the logic analyzer. In a real world environment, the board might be communicating to another hardware device or providing debugging information, so this is one useful way of capturing it. All right, so once we've done our hardware analysis, the next step is software analysis, because most of modern devices today have web interfaces or Windows software that you can use to communicate with it. And so we're going to be looking at executable files, ELF binaries, if it's a Linux-based operating system, which a lot of devices are now, firmware reverse engineering, and trying to extract data from the memory on the device. So our process ends up generating, I know this is probably not legible, but I'll just talk you through it. It ends up generating a database of information about every file that's used in the software for that particular hardware device. So in this case, you're going to get checksums, file sizes, if the binaries are compiled with security protections like memory randomization, any useful strings, libraries that the software depends on, and all that sort of information. From a vulnerability analysis standpoint, this is very valuable information. So once we've cataloged all of the components of the software, then we do assembly level reverse engineering. So in this case, this is for the Medtronic medical device that I pointed out earlier. This is what the flow graph of the software looks like. So every function of the software as it's connecting to pieces of code, this is what it looks like. It's helpful to see that from an attacker perspective. And then you can also find interesting things like when we disassembled this particular software, we got an error pop up in our disassembler that gave us a hint as to where the developer of the software was storing their code and their debugging symbols for that code. So that's this line here. This is something you might be able to go search for on the internet, and if you get this, it'll provide very valuable reverse engineering information. So from a reverse engineering standpoint, we want to identify functions that the software is using to control the device that we might be able to take control of. Such as, let's say you're connected using the manufacturer's software and you want to watch where the software is writing files to your computer by pulling data from the device. Let's say it's a CPAP machine. It's going to be pulling data from the pressure on the hose and writing that to a database file or a text file. And that might be useful from an attacker standpoint to know where that's being written to. So when we do our reverse engineering, we look for all that sort of thing. Same thing for registry keys. If the device writes to registry keys, we want to know about that. We also want to know what the file permissions are, the registry permissions are, service permissions. These are all things that from an attacker perspective we may be able to affect. Probably about 10 years ago, Adobe had a situation where their software would install a service on Windows, and that service had vulnerable permissions. You could then leverage that service to get admin on a computer just by way of them having Adobe installed. Skip all of these. So another thing we end up doing is disassembling Java. Many of these devices are using Java software for control. And when you reverse engineer that, you can find where encryption keys are created, what types of hardware the software is designed to communicate. In this case, they have TDI drivers for USB. We've been able to inject code in these sorts of things and cause effects on the hardware. So that was the static analysis part of our process. Now is the dynamic analysis part. This involves running the software itself and capturing everything that the software does on the computer. File system changes, registry changes, artifacts in memory, processes that get created, network connections, ports that get open. And so we use tools like sysinternals for capturing that information, AuditD or OS Query on Linux and OS X, and then debuggers. This particular screen is I think x64 debug. And in the debugger, we can see the software loading libraries, we can see the functions that get called out of the software, and set breakpoints on these things so that we can watch while the software is doing its operations and pinpoint where a vulnerability might be. So in this case, for that Medtronic software, by setting a breakpoint on a particular function, I think read file in this case, we can see that it's reading in a URL for it to communicate with. So that might be something interesting from a testing perspective. What's at that URL? Can we emulate what that's doing and lie to the hardware, make it do things it's not supposed to do? Okay, so many pieces of hardware now have mobile control. Medical devices do this, home IoT devices. And so we have a process for reverse engineering mobile apps as well. And I'll just talk you through that briefly. First is static analysis of the mobile software. So for Android, it would be APK files. Usually you can find these APK files on a site like APK Pure. Download that, run it through a tool called MobSF, which will give you a report like this that tells you vulnerable permissions that the APK is using, if it has any clear text files with sensitive data, all kinds of useful things like We also use the same disassemblers and debuggers like we would on other types of software. Another thing that we do is injecting a certificate into the mobile device so that we can snoop on the SSL protected communications. There's a tool called APK Man in the Middle that allows you to remove certain configurations that would prevent that from happening, and then you can just watch the traffic going back and forth to the target. We did an analysis of TikTok, the TikTok application, because it was in the press a lot for being potentially a malicious piece of software. And it's a very large APK, and so what we had to do was spin up a huge AWS node with a lot of memory and processor power so that we could break open the APK, remove its certificate protection, inject the certificate, and then monitor all of TikTok's traffic. And the result of that process was TikTok, from a software and network perspective, is no better or worse than any other social media software, meaning it steals everything, just like Facebook does or Instagram. All right, so we've taken care of the RF side of things, we've taken care of the network side of things, and the software side of things. Now at this point we have some ideas of vulnerabilities that we can leverage, things that we can attack. So we build our own tools to make use of that, and we provide these tools to our customers. So if you go to the Red Pro Lab GitHub, these are all free, you can download them. We have tools for doing that file scan that I showed with all of the dependencies and checksums and file information. We have tools for exfiltrating data over HTTP from devices. See if there's anything else that would be useful. A Unix recon tool. So many of these devices are running an ARM processor and some Linux variant. And if you can get this tool on there, it will tell you everything about users, passwords, groups, file system permissions, running processes. It just does that in an automated way and sends it to you. So check those out if you get a chance. These are a couple of examples of our tools in action. I know it's not legible, but this particular tool, what it will do is if you install a piece of software from, say, Amazon, like you have an Alexa, this will record every file that gets installed on your computer, where it goes, what file permissions it gets, what type of file it is, checksums, all of that. And this is a similar example for portable executable files like Windows-based files. Once you have your tools built, you've collected all your data, you've identified vulnerabilities, you want to build a knowledge base. And this is an example of web application knowledge base that we have that we're working on, where we store all of the photographs, reverse engineering call graphs, file information like what I showed you a minute ago from the scripts. So that way you have a central location you can go search every time. I have this component. What devices does it belong to? What vulnerabilities does it have? Is it related to a different device that we can be looking at? And then finally, documentation. If you didn't document it, you didn't do it. Generally, we end up with very large reports, 100-page plus reports with a lot of appendixes containing all this information. And this is what we provide at the end of the day to the customers. And usually the documentation should have roughly 3 audiences: executive management, technical staff, and then other reverse engineers or security professionals, deep technical staff. Executive summary is 1 page, high-level details, maybe 5 pages, deep technical details, 30 pages. And I'm out of time for the case study, but if anybody's interested, I'd be happy to show you offline. At that point, I'm going to open it up to questions.
Hello, I got 2 questions. One is, have you ever done any testing on space system equipment or parts hardware or software? And my second question is, have you ever been shocked or surprised either about finding individual hardware trojans or backdoors, or the amount that you do find?
Sure.
Thank you.
Absolutely. We have tested space-related telematic systems, so the software that's talking to sensors on space devices. We've also tested some sensors that have gone on satellites, for example. Nothing as far as like propulsion or control, these are more scientific sensors. And then as far as surprise, yeah, definitely. We tested a badge reader system that's used in very sensitive places, and the software for the badge reader had a backdoor password, and it was made by a foreign company. And the password was the name of the software. So that was very shocking. We're often shocked with how vulnerable these devices are, but only a few times have we found like an intentional malicious backdoor Trojan in the device. It's actually pretty rare unless you're getting gray market devices from China or something like that. Thank you. Any other questions?
Hi there, Jonathan Vanderdoes, Security Operations Space. Thank you. Interesting talk for sure. Two questions. One, is there an average timeline to the type of contracts you get? And then second, seems like it's really interesting that your company is able to come in and reverse engineer these problems. It seems like perhaps it's a bit after the fact. Can you speak to anything regarding is there intelligence being put into these clients of yours that they might want to have this information before they go and purchase hardware? Is there much work being put in that area?
Sure, absolutely. So it is a bit after the fact. Often we're working with hardware manufacturers themselves, and so in a few instances, such as with avionics equipment, we've been integrated into the production, like the build of the devices. So it's part of the iterative, as they're developing things, we're testing, giving feedback, they're tweaking, we verify it. If it's a customer that's implementing a device, I usually try to dissuade them from hiring us. I say, are you sure that you want us to test this? Because you've already bought it, and we're going to break it, and then you're going to have to do something about it. That's the most common scenario that we see is someone bought something, and then someone said, oh, maybe we should have this tested. And it's kind of, it's good to know that you're vulnerable, but at that point, they've already purchased it. And it's hard to get leverage on the vendors to fix things often from that perspective. We did a test on some electronic keys that were protecting sensitive materials. And the keys were super vulnerable, but they had spent millions of dollars replacing all of their locks and keys. And it was a little bit late at that point. As far as the timeline, I would say, depending on the complexity of the device, 3 months is about normal. For like small IoT devices, we can do those in a week or two. It often depends on how deep the customer wants to go. They want to know what a funded, highly capable adversary is going to do, then that might take 6 months. And I saw somebody over here. Is there another question?